TensorFlow is Google's open source machine learning library. Rajat Monga is the engineering director for TensorFlow, and in this episode we cover how to use TensorFlow, including an example of how to build a machine learning model to identify whether a picture contains a cat or not. TensorFlow was built with the mission of simplifying the process of deploying a machine learning model from research to production. So we also talk about that, as well as how TensorFlow can be used effectively in combination with Google's open source cluster manager, Kubernetes. Before we get to this episode, a few quick announcements. If you're interested in advertising on Software Engineering Daily, send me an email, jeff@softwareengineeringdaily.com. There are more than 14,000 engineers that listen to Software Engineering Daily on a regular basis, so it's a great place to get your product out into the ears of developers or to advertise available jobs that you might have at your company. Also, if you're an engineer that's looking for an open source project to work on, check out Software Daily at softwaredaily.com. This is an open source news and information site about software. It's being led by Jeff Tribble, a member of the Software Engineering Daily community. You can also check out softwareengineeringdaily.com, which is the website for this podcast. You can find links to the Slack channel, my Twitter account, my email. You can find a link to sign up for our newsletter, Software Weekly. And with that, let's get to today's episode. Alooma is your data pipeline as a service. With Alooma, you can create custom analytics with Amazon Redshift. Alooma is a fully managed tool for pulling from different data sources: MySQL, Postgres, Elasticsearch, Salesforce, many others. The code engine of Alooma allows you to write custom Python code over the data stream to clean and enrich your data, and the mapper allows you to control how your data is loaded to your data warehouse. If your schema changes, use the auto mapper to handle that change. To find out more about Alooma, go to alooma.com/sedaily. With Alooma's custom analytics, you have a holistic end-to-end view of your business. Join your marketing data with your Salesforce data, for example, and discern the true value of your online marketing campaigns. Go to alooma.com/sedaily to find out more. That's alooma.com/sedaily. Thanks to Alooma for being a sponsor of Software Engineering Daily. Rajat Monga is the engineering director of TensorFlow. Rajat, welcome to Software Engineering Daily.
Thanks for having me, Jeff.
TensorFlow lets us express machine learning models as directed graphs consisting of nodes and edges. Why is the abstraction of a graph a useful data structure for representing a machine learning model?
So when you look at machine learning models and the kind of complexities that you want to model there, they're really starting to look like programs nowadays. And what a Dataflow graph abstraction allows you to do is really write them as programs, just as any software engineer would. And it's pretty flexible. It's not tied to one specific paradigm of machine learning, say logistic regression or deep learning or whatever. It's a fairly broad, general, programming language in some sense that allows you to model anything that you want.
Creating a computation graph is usually divided into a construction phase where you're assembling the graph, and then an execution phase where a session executes the operations in the graph. So at a high level, can you describe what is happening in each of these phases?
Right. So the first phase, where, as you said, you are assembling the graph by specifying what are the operations you want to do on your data and really putting them together. That's sort of like, if you go back to a programming class, that's like writing your program in an editor, and then you compile it, or in this case, you don't have to compile it separately, but the first time you execute it or try to execute it in your session, it basically compiles it for you. So sort of a very simplified JIT, so to speak. And at the second execution phase, it's exactly like running your program essentially, where that's the place where you give it some data and execute the model, really run that model through over that data. If you're training a machine learning model, then you probably iterate over tons and tons of data. If you are just doing inference or doing a prediction on, say, an example, then you just, go through, do a one pass typically on that graph.
The construction of these graphs, I guess the data structures at a high level that we could talk about are the operations are the nodes in the graph, and the edges are tensors. So between two nodes, you have a tensor that represents a matrix of values that is an input to the next node in the computation graph. And then that node will perform some operation on that tensor and output a different tensor. What are some of the types of transformations that might be run on a tensor input in order to get a different tensor output?
Right. So let me take an example of what typically goes into that tensor, right? Let's take the case of images. So if you have a single image, let's say black and white, then it's really a two-dimensional matrix, just like you said. Now make that a colored image where, the color is represented by red, green, and blue. So you add, another dimension, which is 3 pixels RGB. So now it's a three-dimensional tensor. Now, typically, when you process, you might actually take a number of these together. So say 10 of these examples, 10 of these images together. So that sort of makes it a four-dimensional tensor. Now, typical operations that you might do on this might be when you take an image as an input, you might want to whiten it, as they call it, basically make it something that, so let's say you have an image that's too bright or another image that's too dark. Now, for this model to understand both of those well, one of the techniques that's done is to subtract whatever's the medium brightness for that image, right? So that way they both come to about the same scale. So you might do that as one of the operations. In case of images, another common thing that you do is what's called convolution, which is where you take some kind of a filter, say an edge detector, and apply it to all the places in the image.
So are some of the operations that are taking place in these graphs, are they more like data cleaning operations?
So typically right at the input, you might be doing some data cleaning. Then as you go through the model itself, say in deep learning, that's less true. But typically right after you take the input, there might be some simple data cleaning to be done.
Okay. And when a tensor passes through a node, does the node ever change, or are the nodes stateless?
So most nodes in TensorFlow are stateless, but they don't have to be. Some of the nodes do support the notion of state. There's a node called variable, which manages some memory that has a lifetime as long as your session lives, or in some cases longer than that. And you can modify it as well. A few others that allow you to change state are things like queues, hash tables, and a few others like that.
Okay, so I loved your black and white example, and I want to walk through a slightly more complex example. So let's say we want to train a model to be able to identify whether a cat is in a picture or not. So we start with a data set of 10,000 pictures. All these pictures are labeled as either having a cat or not having a cat. How do you put this data in a format that can be processed by a TensorFlow graph?
Right. So on disk, we have certain formats that we support today where, one of them is called a TF record. You can write simple scripts to really generate data in that format. So it can easily be processed by TensorFlow. That said, what TensorFlow also allows you to do in, say, a language like Python is for you to read the data in any form you want, and in memory, before feeding it in, for an image, it would probably want, say, like I was saying, the black and white image would be a 2D matrix with each pixel being one of the points in that matrix, with the X and Y coordinates. And like I was saying, the way to represent a color image would be to make that three-dimensional, with RGB as the most common one, where you put RGB as another dimension. And then if you're using a mini badge, again, just add one more dimension for the mini badge, which is pretty commonly used for training.
And at a high level, how can we figure out what strategies we should take to determine whether these pictures have cats or not? What are the strategies that we're going to use to put into nodes that we're going to use to program this model?
So, in case of image models, there are certain classes of models that we know have worked really well. And if by strategies you mean what are the kind of big blocks that you have, one of the blocks that's typically used in image models is what I mentioned as convolution. And what that does is it's essentially trying to identify some interesting piece. So when it's learned, let's say each of these, it learns what I call filters. Each filter might learn some aspect of the image. So maybe identifying a vertical edge or a horizontal edge at the very bottom, right? At the very initial part of the graph, just when it's processing images. But as it goes through the graph, it tries to learn higher level abstractions. So maybe the second or third layer in that graph might learn more like circles or squares or things like that. And all the way near the top in this case, you would have a node that's really being able to identify whether it's a cat or not, right? And in this case, for a classification, in this case, a binary classification problem, you might use what's called a logistic regression classifier or a logistic loss, which basically says, okay, I'm going to get some input and then I'm going to give you a probability. How likely do I think it's a cat or not?
Okay. And these different filters that we are creating, are you saying that one filter would map to a specific operation, or would we stack multiple filters within a single operation, a single TensorFlow node?
Right. So we do stack a whole bunch of filters together. We might decide that, okay, say we need about 100 filters for the first layer or the first, just to process the input and get all the kinds of information that we might need. And of course, we're not, in this case, we are learning all of this. We're not saying that, okay, the first filter has to be a horizontal edge, the second filter has to be a vertical edge, and so on. We pick the number of filters that we think are appropriate or enough, and then we just let it learn, right? And each of the filters does not have to be an independent node. In fact, you want to stack as much of them together as possible.
So how do you determine when you should have different operations in different nodes?
So the typical thing is if the same input is going to through n filters, let's say, depends on two things, I guess. One, if you have different kinds of operations. So for example, one of them might be filtering or convolutions, another might be pooling. And those two are different functionalities, so they have to be handled by different kinds of operations. Then they cannot be combined easily.
So mutually exclusive pieces of functionality?
Sure. Yeah, you could, in some cases, you might also decide, to split based on performance characteristics, but that's a more advanced feature, I guess.
Okay. So TensorFlow graphs can also have special edges called control dependencies. And these edges indicate that one node of computation might have to finish before another node finishes. Can you explain what a control dependency is and why it's useful?
Sure. So before I go into the control dependency itself, let me step back and talk about how this whole thing is structured, right? How does this graph gets processed? So if you think of writing, say, a Python program, you write the code up, and the expectation is that it's going to run in the order that you wrote it down in your files, right? And if you have a function call, sure, it's going to go to that function and still run it in that order. With graphs and Dataflow, that guarantee just goes away. It really depends, the ordering depends on really the edges in the graph. So the only guarantee that the graph provides is really, if I have a node that gets inputs from these X nodes, it's going to wait for those nodes to finish and then run them because it needs inputs from those. Now, in some cases, especially when you're trying to do updates to state, you might want to make sure that the update happens before you try to use that value, even if that doesn't happen to be doesn't happen to have a direct dependency in the graph, as you might see. So to support the kind of sequential things that you have in Python because of the state, etc., you might want to add a control dependency saying, you know what, I don't really want to run this node in the graph until I've actually done the update to this input that's coming into this. Of course,
Okay.
This just to add one small thing to it. This is one part that is very powerful and allows users to get exactly what they want. But we're also looking for ways to simplify it, etc., so users don't have to think about these kind of things.
Okay, so this is the sort of the serialization process of a process that might otherwise be distributed and would not have a reliable happens before relationship. What would be an example where we would want to serialize something or a pair of operations with a control dependency from our cat picture training model?
So in most cases, you would not need to use it. So one example that you might do it is if you're actually training this on multiple machines, or you have, where, let's say, two different machines are reading the parameters, computing a bunch of things on these, computing gradients for those parameters on different kinds of examples, and then putting them back together. And before you start the next step, as we call it, the next set of examples, you want to make sure that the update has happened. In that case, you might decide to add a control dependency. But for most common cases, we hope you don't need to do that. We'll take care of optimizing things ourselves.
And for most common cases, does the typical model fit inside a single machine? Are you just using one box to process the entire machine learning model?
For inference, which is basically making predictions, that's very common to have the model fit on a single machine, and you're really just running through it. For training, even though a large number of models would fit on a single machine, you might want to use more than a machine or more than a GPU on a machine just to speed up the training process.
What are the aspects of TensorFlow, a TensorFlow program, that change when that program is spread across multiple machines?
So from the end user perspective, there's not much change. In the sense, the way you specify your model remains the same pretty much. There might be a couple of extra statements that you might have to put in there to make sure that it can support the multiple machines. While running it, again, we provide libraries for you to make it really easy to use these multiple machines or multiple devices on a machine. But there might be a few changes in the code. From underneath the covers, of course, there's a lot more going on. There's all the communication that's happening across these machines that TensorFlow takes care of for its users.
Can you talk some about those things that are being taken care of? What are the concurrency problems that you have to overcome in TensorFlow?
Right. So from, as I mentioned, so now we're taking care of communication across these machines. So going back to the example, let's take the cat example, where I'm using two machines, each of which is processing roughly half the data. And I have, the parameters for the model in one place. These are the things that you're learning. So before processing a small number of examples, each of these machines fetches the parameters. And I'm talking about this process just because it's the most common way people do this. It fetches the parameters, does a bunch of computation, runs it through the graph, computes what I call gradients to these parameters. That's it, which tells them, okay, which direction should we make updates to actually learn things here. And then both of these are going to send back gradients. Now, a simple thing from a concurrency perspective might be, okay, I want to combine these gradients that come from both of these. So, of course, these two machines are running independently completely, so they're going to send these gradients at different times. Now, I need to make sure when both of them are available, then I'm going to combine them together and then apply them to the parameters. Meanwhile, those machines are free now, so they're going to ask for new parameters, and I want to make sure that I've done the update before I send them new parameters. So all of this concurrency stuff, all of the communication and optimizing that and making sure that happens in the right order, all of this is taken care of by the TensorFlow framework itself.
Can you talk some about the workflow of a developer who is tuning a model in TensorFlow?
So do you mean somebody who's already has a model and is tuning it, or somebody
Yes. So a developer, so let's say we've made our cat detection model and we want to improve it. What is the workflow like for improving our model, for adding new measures that just make the accuracy more effective?
Right. So a few things that you might look at. One may be, if let's take the simple case. You have the data, you've trained a model, you get certain accuracy. There are, from a machine learning perspective, there's this concept of overfitting or underfitting. And the idea there is to understand whether your model is large enough to capture all the things in the data or not. And if it's too large, it might learn parts of the training data itself and won't work on a new image as well, because it really tries to fit to the data that it's seen. Whereas if it's too small, it might not learn all the aspects from the data that you have. And in that case, there's the opportunity for you to do better if you increase it. So there are ways looking at curves, especially something that we provide with this thing called tensor board, where you can look at your curves on how does your accuracy look on your data set, and based on that decide if you're underfitting or overfitting. In case of underfitting, you might want to increase the model size. So that's a very common thing. You might want to keep doing that until you hit the point of overfitting. If you're overfitting, then there are ways to improve generalization, applying techniques like dropout or regularization that might help you with that. And then independent of these approaches, there's also this notion of, okay, there are these things called hyperparameters, things like learning rate, things like what is the size of different layers. So let's say I have two different layers. I might be able to, maybe the first layer needs to be bigger versus the second layer, or the other way down. So you might want to try a few different kinds of variations here to see which one actually works better for your case.
Continuous integration allows teams to ship software faster. SnapCI is a continuous integration tool built by Thoughtworks. And you can go to snap.ci/softwareengineeringdaily to find out more. Snap knows all about your Git branches and integrates seamlessly with GitHub. Snap can run your tests in parallel for fast feedback, and Snap allows you to model your build as a sequence of stages, from the fastest tests to the more comprehensive ones. Configure some of your stages to be automatic and some to be manual, in case you want to have more control over your deployment. SnapCI embodies the lessons that Thoughtworks has learned from 20 years of software delivery, the same lessons that have been written about by Martin Fowler and Jez Humble. Check it out at snap.ci/softwareengineeringdaily. Again, to check out snap.ci and support Software Engineering Daily, check it out at snap.ci/softwareengineeringdaily. So when a model gets so big, it has thousands of nodes and edges, when a model gets that big, and you're saying it might start to overlearn from the data and wouldn't work for new examples, it sounds like kind of an accumulation of technical debt. Does it ever get, when it gets that big, what is the process for figuring out the aspects of the model that are not working?
Right. So when you are growing the model, you can, there are different parts to it. One is empirically, you can if you're looking at deep learning, say, and you have 5 different layers, you can slowly chop down the layers or make each of the layers smaller to see which ones help you the most and which ones are not that useful. The other alternative approach from a machine learning perspective is what's called regularization. And what that does is essentially constrain the model in different ways. So it can't really learn overfit on your data or overlearn from that small data set that you provide, because you're restricting it. You're not allowing it to learn everything all the time. In many ways, I mentioned dropout or regularization is 2 of those approaches. And those approaches can also help you. In terms of thinking of it from a software engineering perspective or technical debt perspective, I don't think it's quite the same. There are things that you can do to continue to improve the model even with that. And there are other approaches where leveraging other data sets that aren't the same as your problem, but really leveraging or understanding from those and applying that to your problem as well that you could use too.
Okay, so here you're basically identifying that improving accuracy is not the same thing as debugging. Can you talk a little bit about the debugging process, though? How do we classify what is a bug in a machine learning program, and what are the ways that programming in TensorFlow improves the debugging process?
Right. So a few of the issues that you might see, which are more similar to, say, bugs or crashes in a typical program, is when you put things together, maybe you get infinite values at some point, or nans, or not a number. That's fairly common early on, and a few things that can cause that are, say, your learning rate is too high and you're trying to go too fast, so your numbers become way too large and don't fit in what a floating point number might allow you. So there are, just like software engineering, there are standard techniques for doing that. Like the example I mentioned, the first thing you do is, you lower your learning rate. But there are many other things as well. It's possible that if you are introducing your own new module into there, so like Jeff mentioned, there are these things called operators, and you can write your own operator as well. It's quite possible that when you write that, or when you write the gradients for that, maybe they're not right, and maybe there's a bug in there. So then you go and debug that. In other cases, even if you're using existing things, just like a program, you can go step by step and run parts of it and make sure that what you're getting there is what you might expect at that point. And TensorFlow, given that it's in Python, you can do a lot of these debugging pretty easily. You can print out values at any point. You can log things just like you might with any other programming language. And there are also visualization tools with TensorBoard that allow you to visualize parts of those matrices, etc., and give you a sense of what might be going wrong as well.
TensorFlow is built using the Dataflow paradigm of programming. Dataflow is a paper that was written at Google. What is the Dataflow paradigm?
So the Dataflow paradigm actually goes way back. If you think of how your typical programming happens, like I was saying, you basically execute the way you're writing things, right? The way you write things pretty sequentially. With Dataflow, you can think of as each operation is independent of each other, right? So in some sense, from a programming terminology, you could think of each operation having its own thread or its own processor in some sense. And it can run whenever it has input data for it. So let's say there are 1 or 2 nodes, 2 edges coming into a single node. Now that node, you can think of it as having its own thread or processor. And when data is in there, data comes in, it's available, it processes that. Now you have many, many different nodes in the graph. Of course, there are dependencies in some cases because of these edges. But wherever there are 2 nodes which are not dependent on each other, this automatically makes them be runnable in parallel to each other. So the parallelism is fairly inherent in a data flow paradigm, and that in some ways is where it makes it easier for us to optimize and scale it out to many, many machines.
One of the focuses of Dataflow, as I understand at least, is that it offers tools for helping with event time ordering and windowing. And this is important because streaming applications have data that's coming so fast that if you process it in a naive way, you're going to have events that just come out of order and it can mess things up. But does this event time ordering help within the domain of TensorFlow?
So the Dataflow that you're talking about, basically that Google Cloud implemented and it's available externally as well, that actually supports streaming and batch-oriented models. Today, the way things work in TensorFlow, it's what's called batch-oriented data flow processing. Of course, in this case, it's not like if you have 10,000 examples, you're running all those 10,000 examples together. It's more like when you take one example or a small number of examples, say 100 of these, you're going to run them through the entire graph before you start the next one. So the streaming and event processing that you're talking about is not really applicable today in TensorFlow.
Okay. So what are can you help me understand, what are the concurrency abstractions of Dataflow that help you manage the concurrency of a TensorFlow graph?
So, like I was trying to explain earlier, the graph itself, any nodes that are not directly dependent on each other can be run in parallel. So that's the lowest level, in some sense, the simplest one.
Right.
Now, other things that we can do with this, and that's something that's built on top of the Dataflow paradigm, but in TensorFlow, is now you can split this graph, you can partition this graph in different ways, and have each of those partitions run on different machines, different threads, different GPUs, whatever makes sense for you. And what TensorFlow does is it incorporates as the additional communication wherever it's needed. That's what we call is model parallelism. And that works really well for certain kinds of models where you can take advantage of many devices at the same time. Another form of parallelism that we support and concurrency that we support is what we call data parallelism, which was the example I was talking about in the cat case, where we have, say, two machines, basically the same model. They're going to share the parameters through communication, but they're going to run through independent examples through that exact same model at the same time. So those are three very common kinds of concurrency that we use. Actually, a fourth one is each operation itself could probably be parallelized as well. So taking the case of a convolution example, when you're running it over an image, and let's say you have 100 filters on 10 images or 100 images, so you can actually parallelize that very, very well on devices like CPUs and GPUs, and we take advantage of all of these together to really speed things up.
One of the efforts of TensorFlow is to be able to improve the workflow that a researcher goes through, where a researcher builds an experimental model and then can easily deploy that model to production. This is actually been a pain point for a long time, where a machine learning developer will build a model and then there will be difficulties in pushing that model to production. What is the root cause of those difficulties, and how does TensorFlow address them?
Right. So there are many things that make it hard or that have made it hard traditionally for developers to take something from research or, a data scientist to a production scenario. One of them being most libraries that were written for training models or for learning these were not great for deploying. So maybe your library was in Python, but in deployment you want C++ or Java. Maybe your library was, okay, it would support multiple machines and all of that was great, for training, but at inference, because you're going to run one example at a time, it's going to do a really sloppy job of it, and many such things that come into play. So what we've tried to make here is something that allows us to do research because it provides the flexibility at a higher level, say in a language like Python, but then pretty much the same APIs, the same library can as is run in production as well. So you can take the exact same model without having to do any changes, etc., and really run that in production, integrate it into whatever your production style thing is, right? Because we support, at the core, we are written in C++. It's fairly high performant. There are thin layers in many different languages that you could use to integrate with your application as well. Now, in addition, one more thing that we've added and we've open sourced as well is what we call TensorFlow serving. So what that does is it basically allows you to easily package your model, and we provide the code for serving it as well. So you can just deploy it as a server that you can call out with an RPC and just make calls and get results back as well. So we take care of all of that for you. You don't have to worry about how are you going to serve it, how are you going to manage it. And of course, if you want to run this on Google Cloud, then it takes care of auto scaling and all those things in addition to all just serving as well.
We did a show recently about Kubernetes, and one of the things, it was with Craig McLucky, and he was talking about how Kubernetes was architected from the beginning. Kubernetes is this cluster manager for people who don't know. And Kubernetes was architected with the idea that from day one, the Kubernetes developers knew that it was going to be turned into a cloud service. And there were some advantages of knowing that up front that allowed them to architect Kubernetes in certain ways. Was the same true for TensorFlow?
So from day one, we knew we would be using TensorFlow at Google. In fact, it came from a prior version called Disbelief, which we were using internally at Google. And internally, the environment that we use is pretty much like what you see at Google Cloud. And so, yes, it was very important for this to run in that cloud-like environment. And we always made sure that it's not going to run just on a single machine or a small set of machines, but really optimized for the cloud as well.
And, with software engineering, there's most advanced organizations have a continuous deployment process where if you have a piece of code that you've written, you want to deploy it to production, you can just ship it into a pipeline that will put it through a testing process, and then maybe it'll be released to a certain portion of users, and then gradually it'll propagate to more and more users. You kind of test against the population. Is there a similar workflow to pushing a machine learning model to production where maybe you expose it to just a percentage of the population, you gradually ramp up how that model is being used in production over time?
Yes, that's right. That's pretty much exactly the same as you described. You do want to, with machine learning models as well, you want to follow the same kind of process. You want to make sure you test and validate the models before you push them out. So just like a release process that you were talking about, you maybe want to run it on a different kind of data set. You want to make sure that it handles the same kind of load that you want to handle. And then when you deploy it, you try it on a small set of population, make sure that the metrics that you care about, maybe it's accuracy, maybe it's user behavior, whatever you care about is being met before you actually roll it out to everybody.
Mm-hmm. So we talked a little bit about Kubernetes here. How does TensorFlow work when it's running on top of Kubernetes? Is there any useful synergy between the two tools?
So Kubernetes provides this cluster management solution, like you were saying. And so the basic idea is, let's say you have a number of machines. How do you run TensorFlow on each of these machines and have them talk to each other? You need some way of doing that. Yes, you can do that via your own shell script where you say, okay, I'm going to deploy TensorFlow on this port on these 10 machines, and then I'm going to set this up with this configuration, etc. Using a cluster management solution like Kubernetes makes it easy for you, basically allowing you to manage these processes for you. If there are failures, it's going to take care of those and a number of things like that. Of course, Kubernetes is the one that we've integrated with today, but it's fairly easy to integrate with many other cluster management solutions as well.
So, as you said, TensorFlow is designed for this distributed machine learning process. You can distribute your data flow graph across several nodes. What are the communication primitives for different TensorFlow nodes communicating with each other?
So when we have these different machines and they're trying to talk to each other, what we do is, like I was saying, let's say you have this large graph that we've partitioned. So what we do is when we create that partitioning is wherever we break an edge, we essentially introduce what's called a send and a receive node on both sides. So the send side will have a send node instead of that edge now, and the receive side will have a receive node on that side. Now, they logically have a connection between them, of course, not that doesn't show up in the graph. And the receive node, when it's scheduled to run, it's basically going to do a pull. It's going to ask the node, it has the information, which machine it needs to go to, connect to, etc. It's going to send out a request to that saying, okay, I need this data. Can you please send it to me? And on the other side, when the send node gets the receive request and it has the data available, it's going to send it over.
So you work at Google managing the TensorFlow project. As we begin to wrap up, I'd love to know just some details about how you manage this project. It's such an interesting and unique project. What are you doing day to day, and what does the management of TensorFlow look like?
So, we have a great team here at, being at Google. We have a lot of good engineers, of course, but the team at TensorFlow has been really, really amazing. And the engineers, for most part, I would say, manage themselves. We talk about what are the important things we need to address. We, say quarterly or regularly, we would talk about, okay, these are the things that we want to make future improvements on. This is where we see this going. And engineers have projects that they're working on that they're driving towards. For me personally, I'm also involved with talking to a number of teams that are users of TensorFlow and figuring out if they are really getting what they really want. Are they, are the things we're doing good? If there are issues, how do we address them? How do we make sure the team continues to grow? We've, continued to hire as well. So, talking to new people and things like that. Those are the things that keep me busy today.
Mm-hmm. For engineers at Google who have spent a lot of their time writing models in disbelief, which is the old system of writing machine learning models, do these engineers need to convert their models to TensorFlow, or is it optional? And what is the process of converting a model from disbelief to TensorFlow?
So it is optional. We are making it easier, of course. So there are new things that are available in TensorFlow that TensorFlow is better at, which makes it all the more reason for them to consider moving. Over time, we see more and more of these moving. Not everybody is going to move at the same time, of course. People maybe they have a model that's already running in production, and that's great. So the next time they come around to, okay, they want to process this model, or they want to update this model, or they want to make significant changes to that whole process, maybe that's when they'll come back to this. Or maybe if they want something more out of what they're trying to do, maybe there's new research that we've done in TensorFlow that these teams want to take advantage of, then maybe that's another reason for them to move to TensorFlow. So it really varies. It's across the spectrum. We're seeing a lot of new users on TensorFlow and some existing users from disbelief move over across the board.
Okay, Rajat. Well, thanks for coming on to Software Engineering Daily. I really appreciate your time, and I am a huge fan of TensorFlow. So thanks for working on this.
Thank you, Jeff.
Thanks to Symphono for sponsoring Software Engineering Daily. Symphono is a custom engineering shop where senior engineers tackle big tech challenges while learning from each other. Check it out at symphono.com/sedaily. That's symphono.com/sedaily. Thanks again, Symphono. Wow.